This is the second video, or rather the second part of a video on the subject of the conclusions on energy that I've reached after studying the subject. And I finished the previous video because I'd run almost out of time, and I had got as far as talking about the dimensions of energy and the energy shell, which is the mathematical model that I use to describe how energy works. I may not have made it quite clear enough that when I relate energy to a length of separation between two bodies, the length is what I call the energy equivalent length, and this has to be multiplied by the number of lines of force, or by the product of the masses, in order to give you the total energy. Now that length is a length, it is a length, and the energy depends on the square of that length, and you add the lengths as vectors to get the energies themselves are added arithmetically. You don't add the square of the energy, potential energy, to the square of the kinetic energy. You add the two energies, but you add the squares of the lengths in order to get the total. You're very familiar with that if you're familiar with Pythagoras. So I just mentioned that now so as to clarify that point. I have mentioned it before and clarified it, but I want to make it clear again. Now, I stopped when I got to the equations because I wanted to spend some time on that, and I was almost out of time. Now, the way in which I add these energies is to take the product of the masses, mass 1 and mass 2, which would be the mass of the Earth and the mass of the Moon in the case of those two bodies, and I multiply by the square of the length of the side of the triangle that I'm referring to, and that gives me a measure of the energy, but I want the dimensions to be the same as we are used to, because otherwise we'd have to rewrite a lot of the physics books in order to discuss energy. So this is not compatible with the half mv squared or with Newton's energy, which is the product of two masses times the universal gravity constant divided by the distance. So to make that the same, I've added a constant, which I don't know if it's in use anywhere else. I use K because it was Kepler who first introduced the subject when he said that the period of an orbit squared is proportional to the inverse of the mass of the central body. In this case, it would be the Earth, so if we put make that into a suitable constant, the constant which I call K, I put there for the same reason we have it for Planck's constant with an H, to show that this period is not in seconds per cycle, but seconds per radian. So here K is equal to 1 over mt squared, or torr squared, where that's the period of the orbit. Now that gives you see, that takes away one of the masses and adds the square of time, so now you've got mass times velocity squared, and it looks just the same as half mv squared and so on. There's no half in there. You could put it in, but and it may have to go when the equation's finally agreed upon. This is the length of the side. Now, there are three kinds of sides. There's a time side, which gives you the relativistic mass, and there's the x side as I call it, which gives you the kinetic energy of ordinary movement. So to put them all in there, we have mm squared times the length of the side that represents the total energy, and I put the K in there, equals that, same two masses times the side that is used to represent the potential energy. But since there are three sides, I've got to allow for three sides, and I won't put the sigma in there, but that implies that we're going to add those, all three, so that's 1, 2 and 3. And then the kinetic energy is, what am I doing here? Plus, so I'm going to make that a clear plus, m1, m2. Now to get the length of the x side, you can put x in here, squared, but I'm putting in the velocity squared times the period squared times k. That's the x side, and that gives you the kinetic energy associated with the velocity. Now I'm not saying that this breakdown of potential and kinetic energy is exactly the same. The dimensions are the same, but we have a period in here, and so I'm not saying that this gives you the same number for the kinetic energy, but they still add together. As you can see, if you have the triangles that I showed before, then if you add the longer side squared is equal to the sum of the squares on the other two sides. V squared t squared equals v squared tau squared equals x squared. That's the other side, and that's the equations. Now this has the advantage, you see, that we are using both masses here. Now you may say, well, the mass of the Earth doesn't affect the mass, the kinetic energy. But here we come into a problem that I think that we sometimes ignore, and that is that when we talk about energy, most of the time we're talking about the energy of man-made devices that create energy, such as steam engines, water wheels and so on. Water wheels are man-made, although the water is not man-made, but they are motor machineries. And so we're putting energy in the form of rockets, internal combustion engines and so on, jets. And so this kind of makes us think, well, if I drive a car with a 100 horsepower engine, that has nothing to do with the mass of the Earth. Well, that's true, but nature's equations are to do with the Earth. And if you think of kinetic energy, shall we say, of a rock that's rolling down a beach, that rock may have fallen off a cliff, and the mass of the Earth would certainly affect its velocity when it fell and would affect its kinetic energy. So the mass of the Earth can't be ignored. And as I said when talking about airplanes, that if the Earth had greater mass, the airplane would have to fly faster. And so the velocity is affected by the mass. So the larger the mass, the larger the velocity, but the shorter the time. So they're all interconnected. And so you really should have two masses when you're discussing energy, because it is not a property of a body. A car, the energy of a car is not just the property of the car. It's the property of the relationship between the car and the Earth. It's relative to the Earth. And that's why of an airplane turning in a high wind, where its ground speed will be affected by the wind, the kinetic energy is different from an airplane that's not in a high wind. And if you turn a plane from a headwind into a tailwind, you have got to put in energy, because the wind is not going to blow your plane faster. It's got to go faster to give the same ground speed that you need in order in order to, the kinetic energy you need in order for the ground speed to give you the right kinetic energy for that particular airspeed. And it's not an easy subject to discuss, but it's very important, and those videos, I think, are very important. So here is these are the connections that I'm working on now, and I'm hoping that they might eventually turn out to be useful. By the way, I sometimes call that also the Hooke's equation, or even the Kepler-Hooke equation, because it's very interesting that that same value of mt tau squared gives you, for Hooke's, remember him, he's the scientist who said that when you have a spring or rubber band, or if you consider even the space might be like a rubber band, that this represents the acceleration you get by extending a rubber band a certain distance. So if you this is the acceleration per unit of mass per unit of distance for the rubber band being stretched. So that which leads me to think that maybe gravity and energy, potential energy, is like a rubber band. It may be that what we thought filled a vacuum that caused gravity could be something that's made of rubber or has the characteristics of rubber. It would be interesting if that were true. So this I can call sometimes the Hooke's equation, Hooke's constant, or the Hooke-Kepler constant. So there's the these are the equations, and I hope that they prove of some interest in the study of energy, because energy is not a very well understood subject. I should point out too that the constant K compared with G is more. It's like c, the speed of light, or h, Planck's constant, which is the energy of a photon. The values that go into that are not the period of the particular system we're talking about, but they are the unit values for time and for mass, in the same way as c is equal to length over time. That's 1 unit of space divided by 1 unit of time, whereas G I know is correct when you put in for a circular orbit, if you put in the mass of the Earth, say, and the period of, say, the Moon, or if the mass of the Sun, and a period of any of the planets and their distance, for a circular orbit, you get exactly the value for G of 2.67 times 10 to the minus 11 cubic meters per kilogram per second. So this is not the mass of the Earth or anything, and that's not the period of any orbit. These are fundamental units. And if you do use that, and you then calculate the Planck length and the Planck mass and the Planck energy and the Planck time, by taking those three variables and using simultaneous equations, find out the value of mass in terms of the three natural constants and the value of time and so on, you might get a better value. I have not actually calculated it yet for the mass, which with using Newton's equation you do not get a good value for the Planck mass, because it's much larger than it should be, because it's actually more, I think, than the mass of the proton. So this might be a better third natural constant, but it is a natural constant. Thank you.